I'm going to talk about the midpoint rectangle approximation method. I'll assume you're familiar with the left and right side rectangle approximation methods. If you're not, I would invite you to watch my video on those methods. All right? So let me now do the following example. So give me a minute to draw a picture. All right, so if you wanted to find the integral of x squared from 0 to 4, you could just use the fundamental theorem of calculus. And that would give you 21 1/3. Let's pretend you didn't know that, or maybe for some other reason you wanted to approximate it with rectangles, okay? And assume that you use the following rectangles. Okay, if you used those purple rectangles, you would be using the midpoint rectangle approximation method. Now, the reason those rectangles correspond to the midpoint rectangle approximation method is because the points of intersection of those rectangles with respect to the blue curve correspond to midpoints of line segments with respect to the x-axis. Okay? Let's focus now on the leftmost purple rectangle. Notice that that corresponds to x values between 0 and 2. What is the number exactly in between 0 and 2? It's 1, right? Notice that where that purple rectangle intersects the blue curve corresponds to the point with an x value of 1. Let's look at the middle purple rectangle. That rectangle corresponds to x values between 2 and 3. What number is between 2 and 3? It's 2.5, right? Notice that where the middle purple rectangle intersects the blue curve corresponds to the point with an x value of 2.5. And then for the rightmost purple rectangle, that corresponds to x values between 3 and 4. And what number is between 3 and 4? It's 3.5, right? So the point of intersection of that rectangle with respect to the blue curve, that point corresponds to an x value of 3.5. Now, let's go ahead and get the number that these rectangles would give us for the approximation to this integral. So the leftmost rectangle has a width of 2, and the height is with respect to x equal to 1, so I'm going to use 1 squared for the height. The middle purple rectangle has a width of 1, and the height corresponds to the number in between 2 and 3, the square of that number. So I'm going to use 2.5 squared. And then for the rightmost rectangle, it has a width of 1, and the height corresponds to the square of the number in between 3 and 4. So I'm going to use 3.5 squared. And then with the calculator, you can see that this is equal to 20.5. Okay? If you used the left side rectangle approximation method, with rectangles that had intervals with respect to x that corresponded to the intervals with respect to x of my purple rectangles, you would see that you would get an approximation of 13. If you used the right side rectangle approximation method with respect to 3 rectangles that had corresponding intervals with respect to x, you would see that you get an approximation of 33. Notice that the midpoint rectangle approximation method gives the best approximation. Okay? Let me quickly add that you can't assume that for every integral, any of these methods will always give the most accurate approximation. Okay? Now, I would like you to use the midpoint rectangle approximation method to approximate an integral. I want you to approximate this integral with the midpoint rectangle approximation method using 5 rectangles of equal width. All right, and I'm going to give you the intervals with respect to the x-axis that correspond to the 5 rectangles. All right, so pause the video and do that now, please. All right, so I'll go ahead and do that as well. So I'll start by drawing a picture. And let me draw the corresponding rectangles. Okay, so all the rectangles have a width of 2. And the leftmost rectangle has a height that corresponds to the square root of the number in between 0 and 2, so the square root of 1. The next rectangle has a width of 2 and a height that corresponds to the square root of the number in between 2 and 4, so the square root of 3. Okay, and I can proceed similarly to find an expression for the area of all the triangles. Okay, and then maybe I want to now factor out the 2 and simplify any of the radicals that I can. All right, so I hope that's what you got for your approximation. That's approximately equal to the decimal 21.2. All right, now let me reiterate that you can't assume that the midpoint rectangle approximation method is always going to give the most accurate approximation. In fact, let me show you a graph where the midpoint rectangle approximation method would actually give a very bad approximation relative to the other methods you might be aware of. So this is a contrived example, but suppose there was a graph of a function that happened to have a valley right at the midpoints of that had valleys with respect to the midpoints of your rectangles. Give me a minute to finish drawing this. Okay, what I meant to say was, suppose the graph was such that you chose your rectangles and they each corresponded to an x interval. They each corresponded to certain x values, and you could find the number in between in the middle of those x values. Okay, and so you'd make your height with respect to that middle x value, and if it happened to correspond to these valleys, you could see that you'd get a very bad approximation. All right, so this is just to emphasize that you can't always assume that any one method is going to be more accurate than any other one. It depends on the function and the integral. All right.